Ree, how are you today?
Hi, I'm good. Thank you. Thank you so much yesterday to mention me.
You're welcome.
Very appreciate. Very appreciate. I don't know why. My goodness. Mistake.
I'm going to run down and grab myself another cup of coffee while we wait for more people to pop in.
Sure.
All right, I'll be right back.
Yeah.
Haley, Renee, how are you guys doing today?
Doing okay. How about you?
It's Monday. I want more sleep. I want to sleep. Also, our car broke down at Rhododendron Park in Coopville yesterday. And for some reason or another, my insurance company screwed up the request to get it towed. So it's still sitting down there.
Oh no. Oh my goodness.
Yeah. So we called our Mark's Auto Repair, which is the place we get our cars fixed in town. We're like, is our car there? No, it's not. Okay. So they should have had that done like a day ago at this point. And the tow company that my insurance company is using is not a good tow company, apparently. So whatever. Hopefully it'll get there eventually, or I'll have to go down and try and fix it myself, which is also not great. That was my day yesterday.
What do you think's wrong with it?
I know what's wrong with it. I just don't know how much of that is wrong. So there's at least one radiator hose that has a leak in it. So yeah, problem with the radiator system or the cooling system right now. But if there's one hole, I don't know if that means that there's another one someplace else, or like sometimes that can be a thing where there's more than one leak at once when it happens. So there's a decent chance that if I just change the hoses out myself, I could fix the problem. But also, like, if I don't fix it right, that could, I mean, you can overheat your car and mess it up. So I don't know. I would rather have somebody else look at it than me. So last time we were together on Thursday night, we talked some about solutions, and particularly the big thing that we discussed was that aqueous ionic compounds are electrolytes. Which means that they dissociate to produce ions in solution. So when we dissolve sodium chloride to make aqueous sodium chloride, what we're really doing, that aqueous sodium chloride is actually aqueous sodium ions and aqueous chloride ions. So we split apart that ionic compound into its individual ions when it's dissolved in solution. Because those ions are present in the solution, that's what allows a solution of sodium chloride to conduct electricity. Plain water won't conduct electricity, all right? It's an insulator. But dissolved ions in water allow it to conduct electricity. So we call things that produce ions when we dissolve them in water, we call those kinds of things electrolytes. So besides soluble ionic compounds, strong acids, when we dissolve them in water, are also good electrolytes. Now, the difference is acids like HCl or HBr or HI or HNO3, which is nitric acid, all of these acids are covalent compounds, not ionic compounds. But they can still split apart to make ions in water. So in water, HCl can split apart to form H+ and Cl-. Those are the ions that are produced when HCl dissociates in water. HNO3 would produce H+ ions and nitrate ions. And we could write the same kind of equation for any one of these acids. The point is, strong acids, by definition, also dissociate to make ions in water, all right? As a matter of fact, that's a good definition for what a strong acid is. Why is it so dark in here? Hey, I'm here. Weird. Apparently my camera's not picking up very much light right now. So strong acids split apart completely in water. As a matter of fact, that's how we define what a strong acid is. Any acid that splits apart to make ions in water more or less completely, that's what we call a strong acid. All right. So in general, when we talk about what an acid is something that makes extra H plus when we put it into water. You can see where the H plus comes from in HCl and HNO3. So because of that, the extra H plus in that aqueous solution causes the pH of that solution to go down. So acids tend to have very low pHs. And on the pH scale, anything less than 7 for a pH means that that solution is an acidic solution. So weak acids, and if your acid isn't on this short list, we'll just assume that it's a weak acid. All right. There are a lot more strong acids than these four, but these four are the most common ones that we talk about when we start talking about what strong acids look like in chemistry. So weak acids are different because when we put them into water, they don't split apart completely. Now, does that mean that they don't dissolve in water? No, they dissolve in water just fine. They just don't split apart to make ions that easily. So what I'm going to show you here is an example of one such weak acid. And it's a weak acid that we see in our lab from last week, HCN. So the reason that HCN is an electrolyte is because when you dissolve it in water, it can split apart to make ions. But this reaction, the dissociation of HCN into its ions, is not a one-way reaction like we would think about a strong acid being. Instead, this is what we call an equilibrium reaction, a reaction that can go in either direction. And it turns out that the favored direction between splitting apart and putting back together for HCN, the favored direction is putting back together. So in water, most HCNs are not dissociated. That doesn't mean that when we put HCN into water, we don't get a little bit of H plus and a little bit of CN minus. But it's just a little bit, all right? As a matter of fact, this reaction is not a complete reaction either. The difference is just which direction is favored for each of these reactions. So for example, HCl, if we put a bunch of HCl molecules into water, about 1 billion of them will dissociate into H plus and Cl minus for every one of them that doesn't. That's still a balance, all right? It's a very one-sided balance because almost all of our HCl's split apart. The difference is with a weak acid, the balance is shifted the other way. Most of the acid stays together and only a very small amount of it splits apart. That's the difference between a strong acid and a weak acid. We put a strong acid into water, almost all of it dissociates. When we put a weak acid into water, almost all of it doesn't dissociate. So what that means is, since it only dissociates a little, when we put something like HCN, a weak acid, into water, we get ions, but only a very, very small amount of ions. So this solution, a solution of a weak acid, wouldn't conduct electricity very well. All right, it would conduct electricity because there are ions in that water, but the concentration of ions is very low. We don't have many ions in that water because only a little bit of our HCN splits apart to make ions. So we call things that only make a very small amount of ions when we put them into water, we call them weak electrolytes. Now that doesn't mean that HCN doesn't dissolve in water. It dissolves just fine. It just doesn't split apart to make ions, all right? Now, one thing that you probably have heard at some point, if you've ever had a chemistry class before, is that acids can be very dangerous. So what I want to tell you is that the difference between a strong acid and a weak acid is not the difference between dangerous and not dangerous. There are weak acids that are much more dangerous than the strong acids on this list. The difference really has to do just with whether or not that acid dissociates in water, whether it splits apart. So if it splits apart mostly in water, we consider it to be a strong acid. If it doesn't split apart very much in water, in other words, most of it stays undissociated, then we call it a weak acid. So another weak acid that you're probably familiar with is this weak acid. HC2H3O2 aqueous. So because it's a weak acid, it does dissociate just a little bit in water, but not very much. So the things that we produce when it dissociates are the H+ ion and also the acetate ion, C2H3O2-. So this acid is called acetic acid, the acid that comes from the acetate ion, acetic acid. Anybody know where acetic acid shows up in everyday products that we might use? I guarantee you that more than one of you has used acetic acid in the last 7 days. A lofty claim, but one that I'm pretty sure is correct.
Is that vinegar?
Yep.
So mustard?
Yep. Anything that's got vinegar in it has acetic acid in it. All right. So plain distilled white vinegar is about a 5% solution of acetic acid in water. And it turns out that this type of acid, an organic acid called a carboxylic acid, those kinds of acids tend to have a very tangy flavor to them. So besides acetic acid, which is, tastes like vinegar, citric acid in citrus fruits has that nice citrusy tang to it, right? There are other acids that I could think about. The tang from apples comes mostly from an acid called malic acid, which is also a carboxylic acid. So acids tend to have a very bright, tangy flavor to them. Of course, we wouldn't want to taste HCN because it's incredibly toxic. We wouldn't want to taste any of these strong acids because they also tend to be very corrosive because of their incredibly low pHs. But acids tend to have a bright, acidic flavor, all right? So when you say an acidic flavor, you know what orange juice tastes like, right? That brightness, or you know what vinegar tastes like, that sort of very bright, that bright flavor. That's what an acid tastes like. So both HCN and acetic acid are examples of weak acids. So remember in our lab last week when we were testing the conductivity of the solution, right? Conductivity is just a numerical measure of how well that solution conducts electricity. When we tested the conductivity of our HCN solution, it was incredibly low. Not zero, but very low. The reason why is because when we put HCN into water, it does split apart to make just a little bit of ions, all right? But the concentration of those ions is very, very low. So definitely be able to tell me what the difference between a weak acid and a strong acid is. That's important. And also, we've sort of defined what acids are in the first place. Acids are anything that we can put into water that gives the water extra H pluses. All right, so more H plus in the water makes that solution acidic. It makes the pH of the solution go down. We'll talk more mathematically about that if we have time at the end of the class. Any questions so far? Nothing? All right. So I want to move on to the other major topic in chapter 8, which is the math that we have to do to understand how to work with solutions. All right. So when we talk about the math to do with solutions, what we're talking about is measuring or using the concentration of a solution. All right. So you guys have all heard and used this term before. How concentrated is that solution? Frozen concentrated orange juice. So when I talk about concentration, I'm talking about how much of the stuff that we have dissolved is in that solution per the amount of solution we have. All right. So a concentration generally, mathematically, we normally define it as some amount of solute per volume of solution. So let's think about a very simple example of making a solution and how that would lead to our concentration of that solution. All right. So imagine that we took 5.50 grams of NaCl. And we added it to a 100 milliliter graduated cylinder. So our HCl is sitting down at the bottom of that 100 milliliter graduated cylinder. We're going to add enough water to get all of the sodium chloride to dissolve. And then after that, we're going to fill that graduated cylinder up until the meniscus just touches the 100.0 milliliter mark. So how would we define the concentration of this solution? In this solution, we have 5.50 grams of sodium chloride dissolved in a total volume of 100.0 milliliters of solution. Now, if we actually put these numbers into our calculator and solved, that would give us a concentration of sodium chloride in the solution of 0.0550 grams per milliliter of solution. So every 1 milliliter of that solution contains 0.0550 grams of sodium chloride. Note that the units for my volume in the denominator didn't have to be milliliters. They were only milliliters because that's the way that I measured them. We could convert this concentration into different units of volume in the denominator. We could also convert this concentration into different units of amount of solute in the numerator. All right, so any unit that we can think of for measuring the amount of stuff in the numerator, the amount of the solute, like grams, for example. And for the amount of solution, any volume unit that you can think of. So we could express concentration in units of grams of solute per liter of solution, or milligrams of solute per milliliter of solution, or micrograms of solute per kiloliter of solution. So it doesn't really matter other than how we would measure out our amounts of solute and our amounts of solution at the beginning in terms of what units of amount of stuff and volume we use to express that concentration. As a matter of fact, if we had this concentration in grams per milliliter, we could also convert that into a concentration in grams per liter. All right, so let's say that I wanted to change the concentration units for this concentration. If I have 0.0550 grams of NaCl per every milliliter of solution, how would I convert that into a concentration unit of grams of NaCl per liter of solution? Well, if we remember how to convert back and forth between milliliters and liters back from chapter 1, we should be able to do this math with concentration now. All we need to do is change those milliliters in the denominator into liters. So we multiply by the concentration, or by the conversion factor that tells us in every 1 liter, there are 1,000 milliliters. So my milliliters cancel out in the numerator and denominator, and my new concentration units that are left over are grams of NaCl per liter of solution. We can also express the amount of solute in the numerator of our concentration with a number of moles instead of a number of grams or milligrams. So this particular unit of concentration, moles of solute per every liter of solution, that's called the solution's molarity. Now, we can shorthand it like that. So M with the dash over the top is moles. So moles over liters. That's one way of expressing molarity. We use this concentration unit so often that it gets its own shorthand. All right. So often we'll just express that concentration unit as a capital M. You have to remember that capital M, the molarity concentration unit, is the number of moles of solute per every liter of solution. So if we know the concentration of a solution in grams per liter, can we figure out what its concentration is in moles per liter? Well, sure we can, as long as we remember how to convert back and forth between grams and moles. So if I had a 55.0 gram per liter solution of NaCl, what would its molarity be? What would its concentration be in moles per liter? See if you can solve for that for me. Hold on, you guys, because I've got this tow company out. I got to take this call for a second. So, hello? The danger of restricted numbers. I don't know if it's the tow company or my friend that doesn't like to have his number out on caller ID for some reason or another. All right, so how do we convert those grams into moles? If you know how to convert grams to moles, you know how to convert grams per liter into moles per liter. We know that we can convert grams to moles by adding up all of the atomic masses in that chemical formula to get the molar mass of the formula. When I add up sodium and chlorine, I figure out that every 1 mole of NaCl should have a mass of 58.45 grams of NaCl. So if I multiply this out, I should end up with my new concentration in units of moles of NaCl per liter of solution. My grams of NaCl cancel, and I'm left with moles of NaCl per liter. So I would express the molarity of that solution as 0.941 molar NaCl. If you want to write this as moles per liter, that's perfectly fine. Lots of chemists write it like this all the time. I want you to recognize this concentration unit both ways. When you see capital M, you have to know that that is a concentration unit that means moles of solute per liter of solution.
Dr. Musk,
Yes.
you put the 58.45 gram NaCl. What comes from 58.45?
Where did I get that number?
Yes.
By adding up the atomic masses of sodium and chlorine.
Yeah.
So sodium is 58.44 probably on your periodic table. Is that what you got?
Sodium, yes, 22.99. Okay. Oh, okay.
All right, so sodium is
right.
22.99, and then
Yeah.
chlorine is another 35.45. That's where I got by adding those atomic masses together.
Okay.
So depending on your periodic table, it may end up being 58.44 or 45. All right, close enough.
Okay. Okay, I got it. Okay, thank you.
Sweet. So what we're going to do now is we are going to try and do some math to change concentration units from grams per liter to moles per liter, or grams per milliliter to moles per liter. We're going to mess around with converting from one concentration unit to another. It's really easy as long as you remember how to convert from one volume unit into a different volume unit, and as long as you remember how to convert from a mass unit into another mass unit, so like kilograms to grams, grams to milligrams, or grams to moles, right? So those conversion factors are the same conversion factors we've been using since chapter 1, or in the case of moles, since chapter 5. But in this case, we're going to have to do them using both a numerator and denominator to keep track of our units. All right, so let's say if I dissolve 28.5 milligrams of potassium nitrate into a total solution volume of 354 milliliters, what is the molarity of this solution? In other words, what's its concentration in moles of KNO3 per liter of solution? So we can express the concentration of this solution in the units that we were given to start with. We know that we have 28.5 milligrams of KNO3 dissolved in a total of 354 milliliters of solution. That is a concentration unit. If I put that into my calculator, 28.5 divided by 354, I would get my concentration in units of milligrams per milliliter. Those aren't the units that I want because I asked you to convert them into concentration units of moles per liter. So think about the conversions that are going to be able to take milligrams and turn them into moles in the numerator. And in the denominator, how are we going to turn our milliliters into liters? All right. So if we have milligrams in the numerator, we're going to convert those into grams first and then into moles. In the denominator, we're going to have to take those milliliters and convert them into liters. That's how we're going to end up with the correct concentration units that I asked for here. So it's going to take us a total of 3 steps to do this conversion from milligrams per milliliter into moles per liter. All right, I'll give you guys a minute or two more to work. That's one of the biggest complaints students have about me, is that I always go too fast. I never give people enough time to work and think. It's just because I get really excited and I want to, like, this is so much fun. I want to show you the answer, but you got to figure it out for yourself first, or else it's not nearly as useful. So it doesn't really matter whether we convert our denominator into the right units first or our numerator into the right units first. I'm just going to do the denominator first. We know that if we want final units of liters in the denominator, our conversion factor has to look like this to get those milliliters in the denominator to cancel out. And we know that for every 1 liter of solution, there are 1,000 milliliters of solution, or 10 to the third. Now we can convert our milligrams of the solute into grams of solute. So we know that in order to do that, our units are going to have to look like this. And we know that for every 1 gram of solute, there are 1,000 milligrams of solute. And then finally, we're going to have to convert those grams of KNO3 into moles of KNO3. So that conversion factor is going to look like this. The only way we're going to be able to figure this out is to add up all the atomic masses in KNO3. Has anybody done that? Anybody got a molar mass of KNO3 for me? Renee, what do you got?
Oh, you
Like
know what?
101 something?
Sorry.
All right, let's just do it really quickly. So we have 3 oxygens that are each 16.00. So that's 48 for our 3 oxygens, another 14.01 for our nitrogen, and then 39.10 for our potassium. I'm getting 101.11 grams per every 1 mole for KNO3. So it looks like our milliliters cancel, our milligrams cancel, and our grams cancel, and we're left with units of moles in the numerator and liters in the denominator. So if we multiply this out, that should be the number of moles per liter that our solution is, the solution's molarity. Pretty small number, 7.96 times 10 to the minus 4 moles per liter, but we dissolved only a very, very small amount of KNO3 in quite a bit of solvent, 354 milliliters. All right, so it makes sense that our concentration here in moles per liter is pretty low. So we can also talk about a kind of concentration unit that is given as a percentage. So let's say that I had a solution that was 10.0% weight over volume of magnesium bromide, MgBr2. What that would mean is that there would be 10.0 grams of MgBr2 per every 100 milliliters of solution. In other words, assuming that an aqueous solution has a density of about 1 gram per milliliter, 10% out of that solution would be MgBr. So 10% out of that 100 milliliters of solution would be MgBr. So 10 divided by 100, we take that fraction and turn it into a percentage to get 10.0%. So in general, if we're talking about a percentage weight over volume, To get that percentage, we take our concentration in grams per milliliter and we multiply it by 100% to get a percentage weight over volume for the solution. So can you guys tell me what the molarity of that solution would be? The molarity of a 10% MgBr2 solution. So do you guys see how I get this concentration unit from that 10%? So out of those 100 milliliters, because if we're talking about an aqueous solution, 100 milliliters should weigh 100 grams. Out of those 100 milliliters, 10 of those, all right, so out of those 100 grams of solution, 10 grams would be MgBr2. So the underlying assumption here when we do weight over volume percentages is that the density of an aqueous solution is going to be very close to 1 gram per milliliter. So if it's 10 grams out of every 100 grams for 10%, then it's going to be 10 grams out of about every 100 milliliters. That's what weight over volume percentages do. They assume that the density of the solution is very, very close to 1 gram per milliliter. And I'll give you a second question. So if this one's too easy for you, we'll do something the opposite way instead. What is the percent mass over volume of a 12 molar HCl solution? So we're starting with molarity here and converting to percentage instead of the opposite. I'll be right back. So a 10%, I have to remember to put 10% weight over volume. There are other kinds of percentages, volume over volume or mass over mass. We're not going to worry about those for this class. If we have a 10.0% mass over volume or weight over volume magnesium bromide solution, that tells us that this solution would have 10.0 grams of MgBr2 out of every 100 milliliters of solution. Remember that in aqueous solution, 100 milliliters of that solution would weigh very close to 100 grams. So that's where we're getting the percentage from. 1/10 of that solution is MgBr2. Can we convert that into a molarity? Well, sure we can. All we got to do to make that happen is convert our grams of MgBr2 to moles and convert our milliliters of solution into liters of solution. In B, we're starting out with the number of moles per liter. And remember how we get to a percentage, all right? We need to be able to convert this into units of grams per milliliter. And then after that, multiply by 100% to get our mass over volume percentage. So how are we going to convert our moles per liter into grams per milliliter? We're going to have to convert our moles into grams. We're going to have to convert our liters into milliliters. And then whatever we get for that answer in grams per milliliter, we multiply by 100% to get our mass over volume percentage. All right, take a couple of minutes, see if you can get answers for both these. Hello?
Dr. Musk, just to clarify that unit of measure, the molar, is that what you called it?
Sorry about that, you guys. Oh no, did everybody leave, Ree? Ree, are you there? I didn't lose my class, did I?
I'm here.
Did everybody else just leave? They left?
I don't know. Renee, she had a question for you, one question, but I don't know why they left.
Bummer. I hope they're not upset at me. I had to talk to the towing company. They called and couldn't find the
Yeah,
vehicle.
I don't think they upset. Maybe they thought they thought maybe you gone.
No. I was just leaving
I
for a
know.
second. Oh no.
Oh
All right.
no.
Well, I guess we'll go through and solve these two and get them on tape. And then
Right.
after that,
Yeah.
if nobody shows back up, then we'll just be
So
done.
I did A is 0.543 and B is 43.8%.
Hold on, 0.543. Is that what you said?
The A is 0.5431. So
Okay.
I thought
And,
three figures.
all right, we'll get your answers down, but we'll solve also. And what
Yeah,
did you get
sure.
for the percentage?
And the percentage is I rounded, so 43.8%.
All right, well, let's check your answers here.
Sure.
So I'm going to convert my milliliters into liters. I know that there are 1,000 milliliters in every 1 liter. And then I'm going to have to convert my grams in the numerator into moles. All right, so 24.31 plus 79.9 times 2. I'm getting in every 1 mole of MgBr2, 184.1 grams of MgBr2.
Yep.
All right.
Yeah.
Yep, I'm getting the same thing that you are, 0.543
Yay.
for our molarity of that solution. That's the concentration unit in moles per liters. So if we want to convert to a percentage, then we've got to convert to grams per milliliter, and then whatever that number is, multiply it by 100%. All right?
Yeah.
So let's do it.
Yes.
12.0 moles of HCl per liter. I'm going to convert to milliliters first. In every 1 liter, there are 1,000 milliliters. And then in every 1 mole of HCl, there are 36.46 grams of HCl.
Yeah, I did 3.458 gram.
I'm getting 35.45 for the mass of chlorine and 1.01 for the mass of hydrogen. So that's where I got my 36.46 grams.
Yeah, you rounded 4.6, right?
Right. So if you use a periodic table with more sig figs, then you may get something slightly different, but it'll be very close to that.
Right.
I'm using the same periodic table that we use for our exams, not the Alex periodic table.
Okay.
And then we have our concentration now in units of grams per milliliter. So whatever that number is, I'm going to multiply it by 100% to get my percent mass over volume for the solution.
Okay.
And I am getting 43.8% mass over volume. So Ree, you did both of them correctly. Good job.
Yay.
So that's one of our really big jobs when we look at concentrations, is being able to take one kind of concentration unit and turn it into another kind. So the three main units that I want you to be able to convert back and forth between is a mass over volume concentration unit, grams per liter or milligrams per liter, or a number of moles per liter, so a molarity. or a percent mass over volume. So hopefully with a little practice, and Alex has more of these kinds of practice problems, you'll be able to convert from one of these concentration units to another. That's our big job for this part of the class.
Okay.
Okay.
Gotcha. Yes. Thank.
All right.
Sounds
So
good.
since I lost the rest of the class because I had to take that call about the towing company, I guess that's where we're going to end class for today.
Okay. My
right.
goodness.
Have
Okay.
a wonderful rest of your day.
You
Rita.
too. Thank you.
Yep. Bye-bye.
Bye. Bye. Bye.